So last lecture, we talked about this idea of approaching, getting forever and ever closer to a number. And then we took this idea of approaching and we kind of plugged it into a function to get this idea of a limit. Now, if we investigated further into the limit, we would find that it has many properties. But we're not going to do that investigation, but we are going to check out some important properties here moving forward. And one of them has to do with polynomials. Polynomials, I like to say in calculus, are our friends. They're always simple to work with. And here is one reason why. Let's say we have a polynomial. Now, this can be any polynomial. I'm just going to have one graphed here. And we're going to choose any point on this polynomial. And we're going to find the limit. So I'm going to use this notation here, P, to mean polynomial. So if we take the limit of any polynomial as x goes to c, where c is any point we want to choose, it turns out that this is always equal to the function notation. So in other words, the limit of a polynomial is always equal to just plugging that number into the polynomial. So the polynomial I have graphed here is this x cubed minus 4x squared plus 2x. And let's say we want to find this limit as x goes to 1. Well, what this equality is saying, if you want this limit, then just plug in the number, because this is a polynomial, means you can just plug in the number, and that's your answer. So if we're always dealing with a polynomial and we want that limit, we can just plug the number in. Now, there are other properties of the limit that I'm just going to flash at you here, and here they are. These are other properties of the limit that we're not going to really spend any time on in 213, but it is important to understand that all these properties are kind of working behind the scenes here to allow us to do what we're going to be doing here going forward. And what we're going to be doing going forward really is that if we can plug a number in and get a number out, then that is our limit. And there are exceptions to this, which we will talk about in some further lectures. But for now, and the homework problems that we're going to be doing, when you're doing a limit, if you can plug your number in and get a number out, then that's your answer. So for example, let's say I have this limit here where we got an x square root of x in here, minus 2x cubed, 5x minus 1. And we want this limit as x goes to 1. And what I'm saying here is, if you can simply plug in your number, so I'm just plugging in 1, and if we can get an answer from that, then that is our answer. That is the limit. So let's check out another one. Let's say we have this rational function. So rational function is a polynomial divided by a polynomial. And let's just plug the number in. Now, if we plug the number in here, though, something unusual happens where we get this 0 divided by 0. And 0 divided by 0 is not the same thing as 1 divided by 0, or some number besides 0, like 10 divided by 0 or a million divided by 0. 1 divided by 0 is undefined. That's different from 0 divided by 0. 0 divided by 0 is considered indeterminate, meaning we can't determine at all what the answer is here. And when you're in an indeterminate form, there's something more you can do to get out of that. And that's what we're going to talk about going forward, since I think every one of your homework problems is in the indeterminate form, meaning if you just plug your number in, you're going to get 0 divided by 0. And you're going to have to do something to get out of that indeterminate form so that you can get the answer for your limit. And that's going to be factoring. We're going to be factoring to cancel out terms so we can get our answer for a limit. So let's check out this example again that we just did, which was 0 divided by 0. So we're in an indeterminate form here. We're going to factor the numerator. And now that the numerator is factored, we have these x minus 1s that can divide out. And then we're just left with x plus 2. And now we'll try to plug our number in again and see what happens. And if we plug our number in, we get our number out. And that's our answer. Our limit here is 3. So before we got 0 divided by 0, we plugged 1 in. But by factoring the numerator, canceling out some terms here, we find this limit is actually 3. So check this out for the first lecture question here. What is this limit? So we're going to factor. So if we look at the numerator and factor that, see we have some x minus 3s here that will divide out, and we'll be left just with x plus 1. Now we'll check our number again, and if we plug in 3, we get a number out, and that's our answer. This limit is 4. So check out this one. What is this limit? So again, we're going to factor the numerator. And we can see now there's an x minus 7 that will divide out. And we're just left with x plus 3. We'll check our number again, see if it works. And it does. And we get our answer of 10. So what's happening here? Well, we just did 3 examples of factoring. And here are the examples that we just did, all 3 examples. And notice, I'm going to rewrite these. If I rewrite all these examples, they look like they have a very similar structure. And they do. All 3 of these examples have this structure. And why is that important? It's mainly important because of this part right here. This x minus c divided by x minus c. This is a whole. So in the last lecture, we did some functions that looked like just a normal old function, but then all of a sudden it's at a whole somewhere. That's the result of this term right here, this factor actually. That causes a whole. And so what we just did with these problems is we just solved the limit for a function that has a whole. So the other limit we want to talk about, so we just talked about how to solve a limit at a whole. We're going to talk about now limits at infinity. And the book talks about an approach that is perfectly fine, works perfectly well. I think there's a better way that'll serve you better in the future, though, and that's to actually talk about dominant terms. And a dominant term is always the term that has the highest exponent. So if we look at this limit here, Now again, these are limits to infinity, so notice we're going to infinity now. So that means x is going to get forever and ever larger. So we have an x squared and an x to the first power. The dominant term here is x squared because it's the larger exponent. And what do we mean by dominant terms? The key here is to remember x is getting extremely large. So imagine x is 1,000. So if we plugged 1,000 in here, we have 1,000 squared plus 1,000. Now 1,000 squared, x squared is 1,000 times larger than this. That's at 1,000. However, let's say we go to 1,000,000. If we plug in 1,000,000, then x squared will be 1,000,000 times larger than x. And if we plugged in 1,000,000,000,000, x squared would be 1,000,000,000,000 times larger than x. So when x starts going to extremely large numbers, these exponents start to make a huge deal. And even one exponent away, so this is 1, this is 2, even that difference of just 1 is a huge difference when numbers get large. And when numbers get extremely large, that means that what isn't the dominant term just becomes negligible. And so this limit is actually the same thing as just the limit of x squared. These limits are the same because as numbers get so incredibly, insanely large, this little thing right here just becomes irrelevant. It doesn't contribute anymore in any significant way. So again, the dominant term is the term with the highest power. And what we're going to do is we're going to choose the dominant term and then ignore everything else. So check this out. Here's just a regular old polynomial. What is the dominant term here? Well, we look for the one with the highest power. 10 is the highest power, the highest exponent. And so the dominant term is minus 2x to the 10th. This term will crush everything out of existence as x goes to infinity. So check this out. For question 3, what is the dominant term? So 20, our highest exponent. And then so the dominant term is plus 8x to the 20th. So how are we going to use this? Well, here's our limit going to infinity. And here we have a rational function. So it's a polynomial divided by a polynomial. And we're just going to look at dominant terms because when x gets insanely large, all these smaller terms will get crushed out of existence. They're just going to be, their contribution is going to be so small it's not going to matter anymore. And so we can rewrite this limit then with just the dominant terms in the numerator and the denominator. And then we can simplify. X cubed divided by x squared is x. And as x goes to infinity, well, then x goes to infinity. And so this limit is infinity. Notice we got infinity when the dominant term was in the numerator. And that will always be the case. If your dominant term is in the numerator, your limit will always be infinity. And again, I can't stress enough, this is only true when x goes to infinity. So these are the limits at infinity. Check out this one. So we're going to look at the dominant terms. How do we know when to look at dominant terms? When x goes to infinity. So we'll look at the dominant terms, and we're going to realize that these smaller terms are just going to get crushed to being negligible contribution. And we're left with x squared in the numerator, x cubed in the denominator, the dominant terms. This simplifies to just 1 over x. And here may be something new, but the limit of 1 over x, remember, x is going to get forever and ever larger. So 1 divided by 10, 1 divided by 1,000,000, 1 divided by 1,000,000,000,000. This is a number that's going to 0. And so this limit is going to 0. Now, I could get in trouble for saying what I'm about to say here, but this isn't mathematically correct, but I do think it helps your brain in remembering some of this stuff, that 1 divided by infinity equals 0. Now, again, this isn't mathematically rigorous. I could get in trouble for saying that because technically you have to have the limit word on here. But just to help you remember this limit here, this limit is kind of saying 1 divided by infinity equals 0. And notice here that when the dominant term is in the denominator, the limit 0. And this is always true. If the dominant term is in the denominator, your limit will always be 0. So if you're thinking ahead here, our first problem had dominant term in the numerator. This problem had dominant term in the denominator. And there's only one case left. And that's when the numerator and the denominator have the same dominant term. So if we look at this, we'll get rid of everything except the dominant terms. We can see now that these x cubes will cancel, and we're left with just the limit of 7. And this is a common mistake beginning calculus students make when they see something like this. And I can't stress enough that the limit of a constant is always that constant. It doesn't matter what x is approaching. It doesn't matter. The limit of a constant is always that constant. So check this out for question 3. So now, I know you may have just seen this for the first time, but if you remember, the dominant term is in the denominator. If the dominant term is in the denominator, then this limit is 0. So we'll choose the dominant term. So the dominant term in the numerator is x cubed. Denominator is x to the 5th. Get rid of everything else. X cubed divided by x to the 5th can simplify to 1 over x squared. And here we have this again. We have a limit that's like 1 over infinity. And 1 over infinity is something that's going to 0. So check this one out for number 4. So in this case, the numerator and the denominator have the same dominant power. So we'll get rid of everything that's not dominant. Reduces this. We can simplify because these x to the ace will divide out. 12 divided by 4 is 3. And so we're left with the limit of 3 as x goes to infinity. And burn into your brain, the limit of a constant is always that constant. So in summary, what we just went through here is ultimately we went through, we solved two types of limits. The first limit we talked about were whole functions. So that's where you had just a regular old function that just has a hole sitting in it. And we talked about how to solve those specific types of functions, those whole functions. And we did that by factoring. So we solved the limits for those whole functions by factoring and then divided out terms. And then the second one we did was limits at infinity. So if x goes to infinity, we can solve those by using dominant terms. So just choose the dominant term in the numerator and denominator, get rid of everything else, simplify whatever you can, and that'll give you your answer. And finally, I want to say here that in solving limits, that the limit still has a lot of similarities to function notation, but there's also differences. But overall, in solving a limit, the easy thing to do is to simply plug in the number as if it was like function notation. Because a lot of the times, the limit works just like function notation does. So if you can plug a number in, and get a number out, then that's your answer. And the part I need to stress is that this is not always true, though, because the limit does have differences from function notation. But for the homework we're going to do right now, this is always true. You can plug your number in, and you'll get a number out, and that'll be your answer. And then moving forward, because I'm saying here this doesn't always work, and moving forward, we will talk about cases, though, where this does fail. But for now, that's the easy thing to do. And that's the end of this lecture.